Thank you, Alan. Of course, what's missing in that introduction is the coincidence that two astrophysicists in a row and standing in front of you. So my talk is primarily about the streaming data analytics we will want to do on the Internet of Things. And of course, we heard some really good tools this morning already when Stephen talked to us. Some of the sort of the computational things you want to do on data, but to get there, you have to have computable data, which is what we hear a lot about when we come to these conferences, which is a very important aspect of the data science that we do, which is taking these streams, which might be unstructured data, it might be video, it might be text, it might be social media, it might be anything, and turning it into something that we can compute on. And so the assumption in the talk today is that you've done something already to prepare your data for computable algorithms to work on it in a computable fashion. And so the application systems will be numerous mentioned here. And I'll give three use cases, and two of the use cases will be metaphors, and you'll understand what I mean when I get to those metaphors. And that is, one will be an astronomy example, one will be a planetary science example. And the point of those examples is not that I'm teaching you astronomy or anything like that. These are metaphors for the dynamic streaming data that you may encounter in whatever applications you're working in. So we live in this world where more and more things are becoming connected. We call this the Internet of Things, and this Internet of Things is not just a network of things connected through these network protocols, but also that there's actually streaming data between these things. Okay, so we're collecting data from people, processes, objects, events, all of which are creating data from which we can make discoveries and take decisions and improve our processes in our businesses, whether it's financial services or healthcare or whatever. So the broad world of Internet of Things is sometimes now called the Internet of Everything. Okay, so the Internet of Everything is listed here, which you can't even read the details here, but it includes things like transportation and housing and industry and healthcare and IT networks and the energy grid and so on. So we're facing numerous challenges in this new world in which we have so many things connected and so many things generating data. So I take advantage of sort of the historical language around big data, where we have the 3 V's of big data, which of course we don't want to hear about when we come here, but I talk about the 3 E's of Internet of Things, specifically just to highlight challenges that this Internet of Things is going to bring to us. And that is, first of all, everywhere a sensor. That is, everywhere you turn, there's a sensor, whether it's your health wearable device, your smartwatch or your Fitbit or something like that, or the items in your home have little Wi-Fi's or personal area network, so what we call Pi-Fi. So you have this personal internet of information exchange between devices in your home or your local environment. And so we'll have a sensor essentially on everything. And in doing so, therefore, we're quantifying and tracking life and processes and things both in space and time. So it's enabling a world of discovery, but also that discovery has the sort of the negative aspect, which is this third E, which is the erosion of privacy. Okay, so maybe you don't want people to know where you're going or what you're looking at or what you're shopping for and things like that. So there's a lot of discussion that can be had around that aspect of it. That's not the discussion specifically today. Today is more focused on the sort of the science side of this, of what kind of discovery can we make, what kind of application algorithms can we apply to that. And so the challenges from the data perspective are these three. We call them the 3 V's of big data, but I want to focus specifically what I call the deep, wide, and fast data. Okay, so by deep, meaning we have, since the sensors are tracking so many different kinds of things, we're getting a deep view of whatever the thing you're tracking, whether it's your customers, how they behave online, whether it's processes in your manufacturing plant, machines on an airline, like the engines on an airline, or any kind of supply chain. It's the movement of your products. So we have sensors on everything, and we're getting this deep view of how our process or our business or the system is operating. So we have this deep data. We also have wide data. By wide, we mean this in the context of high variety. That is, it's very complex data. It's video, it's images, it's sound, it's text, it's documents. It could be data tables or it could not be. We have many different data types, and they're coming at us in many different ways. So this diversity and complexity of the data is an enormous challenge of how do you fuse and make decisions off of this mixture of different types of data. And then fast, referring to the fact that we're basically sampling at maybe a completely different rate for each device, but we're sampling in time all of these data. So we don't just measure something once and walk away. So you might say sort of traditional demographics, for example, credit scoring when you go to the bank and they decide whether to give you a student loan or not. They may look at sort of your age, your gender, what kind of college education you're working toward. Things that nowadays we would just say that's not really a very smart way to make a decision, but it's based upon static data, okay, things that don't change. Okay, so now, as we heard this morning about the real-time bidding on ad placement, really great talk. I hope you saw that this morning. I mean, these are sort of microsecond decisions, or very fast decisions based off of data that's extremely dynamic, and millions of such decisions made every second throughout every single day. So dealing with this time series data is yet another aspect of the Internet of Things challenge. So you really can't just have a backup plan, all right? So if you're doing credit scoring on your customers, for example, in a financial institution, your backup plan might be you'll get some data off of public sites, okay? So you'll find some public information about your customer, whether or not they should receive this particular loan or credit score or whatever. In the case of Internet of Things, the whole point of Internet of Things is that you're dynamically monitoring something, whether it's your health or a cybersecurity environment, or manufacturing on a plant floor, or an engine on an airplane that you happen to be flying at this moment. You don't want to know that engine passed its test 5 years ago. You want to know now, is this thing operating efficiently and properly? So all this, there's really no backup plan. So with fast data, you really have to have sort of fast analytics that are smart to deal with the data that you now have. So fortunately, we have all these challenges, but there's also a great benefit from all of this. And again, to keep with sort of the play on words here, but again, the play on words is just basically a mnemonic way of remembering these things. So I call it the 3 D to Ds, okay? Data to discovery, data to decisions, and data to dollars, or data to dividends, however you want to call that. Okay, so the real benefits of doing these things with data, as we all know, which is why we're here, we already know this, okay, but we're going to see this even amplified in the Internet of Things world, is that the ability to make new discoveries, make better decisions, and to create new business value, new innovation, is just being amplified as well as the data itself. So there's many use cases, and I want to read this slide to you. It's an eye chart. But there's many examples, whether it's in healthcare or retail or marketing or smart cities or smart highways or smart education or precision medicine, and the industrial Internet of Things, where you have these sensors on the manufacturing plant floor, or is it in your supply chain or wherever. All of these different use case examples come down to sort of what I call the 3, or the XYZ, excuse me, of IoT. And the XYZ is that it's smart something, or precision something, or personalized something, okay? Smart cities, smart highways, personalized education, personalized medicine, personalized marketing, targeted marketing, okay, precision medicine, precision farming, okay, precision wine growing. Did you miss that on the previous slide? So precision wine growing, okay, talking about the specific care and feeding and nurturing and planting seasons and specific plots of land where you plant certain seeds and how you handle that. Okay, so all this data is now being collected everywhere. Let's make the best use of it. That's sort of the general idea. And so the real business value, the real business benefit that's going to come out of this is sort of this very precision way of making decisions, precision way of doing delivery to customers and to clients, or to your business application areas. That's what's being enabled here. So we live in this interconnected, dynamic world. Okay, so from this vast universe of possibilities, like I said, I'm going to give you a few examples. So the big challenge that comes out of this, of course, is doing the streaming data analytics. So that's sort of the message here. And I just want to give you a couple of examples of this before we move into the metaphors, because then when I'm talking about astronomy and planetary science, you're going to say, what were we talking about again? Okay. And so these streaming data analytics examples might be something as simple as, and I say as simple because it's sort of in your back door or out in your backyard that you find already, and that is web analytics. Okay, so traditional web analytics is a lot of times it's sort of hindsight. Okay, sort of what happened. Okay, business reporting tells me what happened last month. Okay, so many site visitors, so many people clicked on this, so many people clicked on that. But all of data analytics now is sort of moving beyond that descriptive analytics phase to more predictive analytics. That is what will happen based upon the patterns I see. to prescriptive analytics, which is how can I achieve the best possible outcome, not just the predicted outcome. And so in marketing, for example, we see how people, in digital marketing, we see how on-site visitors are moving through your web property. For example, if you have an online store, you want to see what they're looking at and maybe make recommendations of products to buy. If you're running a federal agency, the site visitors might be citizens, or it might be other agencies who are looking at your reports, the data you're providing, whatever sort of policy decisions you're making. People are looking at things on your site, and you want to say, well, gee, they seem to be interested in this. Maybe we should recommend they look at this report or this document or this data set. Okay, so this whole sort of dynamic way of interacting with your customers and your clients is changing, and that's just one example of this type of behavior, which we're familiar with all the time. But now we're seeing this advance into all these other use cases. So these use cases may include health alerts. Okay, so real-time discovery. So we heard about Google flu trends before in the past, where based upon people's searches for flu symptoms in Google was able to predict it ahead of the Centers for Disease Control, the outbreak of flu. And of course, there's been all kinds of stories about how that didn't quite work, because sometimes people did that search just because they were interested in learning about something about flu. They heard it in the news, now they're doing a search. It doesn't mean they have the flu. But now with electronic health records, we're having sort of like almost real-time sort of ability to capture symptoms and diagnoses and treatments that have to do with particular types of diseases. And so this is creating now a data stream that can be mined. Now, maybe not mined by you and me, but by healthcare professionals at the National Institutes of Health or Centers for Disease Control or wherever. So electronic health record monitoring to generate health alerts, maybe even tsunami alerts if you're talking about sort of geophysical signal processing and signal alerting. Cybersecurity alerts, obviously we want to be careful about those. That is, when we start seeing people tending toward doing something bad, let's not wait till they do something bad, let's stop it before it happens. Social event mining, people talk about social listening quite a bit. Social listening is applicable in a lot of settings, not just sentiment analysis. Did people really like that Coca-Cola commercial during the Super Bowl? I mean, that's fine for Coca-Cola. They want to know the answer to that question, but most of the rest of us don't really care that much. But social listening might have more to do about what's the sentiment of Baltimore today. Okay, so there's the first sort of arraignment discussions today about those 6 police officers who were being arraigned on the death of that person. Okay, so that's in the news today. Okay, there's all kinds of stuff happening in Baltimore today, and so you maybe want to get the sense or the mood of the population. All right, so that kind of thing is important for a lot of different reasons. Preventive fraud alerts, certainly in any kind of financial transaction, whether it's in commercial banking or financial services, or maybe in a federal agency that's doing payment disbursement, like for example, Medicare payments, Veterans Administration payments, whatever. Can you capture the fraud, the attempted fraud before it happens? Predictive maintenance alerts from machines, infrastructure monitoring from ubiquitous sensors everywhere. So these are all sort of general statements of things that we want to try to do in many different application areas, but it sort of comes under this umbrella of risk mitigation, I would say. So the real business equation we're trying to balance here is the risk versus reward. Okay, so how do we achieve the reward given all the risks that we face with the erosion of data privacy, but also the risk of if we don't monitor these things, if we don't have good analytics, we're going to miss some big event. We're going to miss the tsunami. We're going to miss the outbreak of flu. We're going to miss the cybersecurity intrusion on our network. How do we sort of balance that? So this is what I now call these 3 D to Ds, which is this whole aspect of what are we using this data for anyways? What's the point? I mean, I've often given this talk to people who, in the early days when we first started talking about big data, a lot of times people would just react to the word big data. I said, oh, this is just nonsense, okay? And yeah, there was a lot of hype around big data, and a lot of it probably was nonsense, okay? But people sort of missed the real key point there, which is we're using this data to do something, to make discoveries, to make better decisions, to improve the value of our processes, increase value and innovation within our organizations. So this is really what we're trying to achieve here. So from the machine learning and data science perspective, I like to see at least these sort of 4 sort of applications, machine learning applications, somewhere in your IoT pipeline, somewhere in your data analytics pipeline for that streaming data. That is, can you discover behaviors? Okay, can you discover when something is different? Okay, so this is class discovery. Okay, so class discovery, sometimes it's called clustering or unsupervised learning or segmentation, different words like that, but it's finding the new behaviors, finding the new things that are happening. So if a colleague of mine is doing this kind of class discovery process on something which is not exactly Internet of Things, but could be construed as Internet of Things. Okay, so he's doing a very simple math problem, but the math problem has an application, and his application, which is not what he's doing the math problem. The application is identifying individuals in airports through all the surveillance cameras throughout an airport. So imagine a very large airport, lots of surveillance cameras, probably 1 million passengers a day go through there, and identifying each passenger at each location and time where they are in the airport during that day. Okay, so that requires facial recognition software and all kinds of stuff like that. And then you got to connect the dots. That is, this person went here, that person went there. Okay, so there's a lot of things going on there. Once you've connected those dots, you now have trajectories. Okay, so you may have 1 million passengers. That means you have 1 million trajectories of people moving through your airport each day. And most of those trajectories are very similar. Okay, so class discovery, there's a certain class of airport passengers. They go through security, they go sit at their gate, and they stay there till the plane departs. Then there's another class of people who find their gate, then they go to Starbucks and get a coffee, then they go back to their gate, and then, oh, by the way, I had too much coffee, I gotta go to the restroom, then I go back to my gate. So there's another pattern of behavior. So imagine if you found a pattern which is an air passenger is walking back and forth between the domestic terminal and the international terminal. That's not normal. In fact, not too many people do that. Maybe the security people do that, but not normal airline passenger. Okay, so that's discovering a new kind of behavior, a new class of behavior. So class discovery is of that type. It's not just classes in some kind of three-dimensional plot, and you say, oh, these points are clustered over here, that's a new class. It can be in a graph space, it can be in a video space, it can be in a time series, trajectory space, or whatever. So class discovery is something you should be looking for, finding new things, new emergent behaviors. So in cybersecurity world, they talk about the zero-day virus, right? That is the thing that doesn't exist until today, and by the time you know that it exists, they've already stolen your data. Okay, so there is no model. McAfee doesn't have that in their model, right? Because they haven't seen that one before, and now they put it in their model tomorrow. But oh, it's too late because your data is gone today. Okay, so can you identify those new behaviors, those new classes right away? So class discovery. The next one is correlation discovery. Okay, so correlation discovery I like to put under the moniker predictive power discovery. So what a correlation does, hopefully, if it's not a spurious correlation, which this gentleman here can tell you all about, Tyler Gibbon. So the spurious correlation is a problem when you're trying to identify whether there's a causation or sort of explanatory factor there. But beyond that, if you do see a correlation in your data, besides trying to understand why it's there, that correlation can now be used in a predictive fashion. Okay, so you're discovering the ability to predict the future when you see a correlation. So when you see A correlates with B, and then you see A change a certain way, then you can expect B to change a certain way. So finding these patterns and trends and behaviors in their data is yet another thing we want to get out of our streaming data, to identify those trends and correlations and then be able to make a prediction. Okay, because that prediction may indicate that an engine failure on an airplane or a plant machine failure on the manufacturing floor. Okay, so you want to find those trends, okay, find those correlations so that you can get the signals early and respond accordingly. So those correlations, those patterns, what I say is sort of represent the DNA of whatever system you're monitoring. Okay, so the DNA, when your DNA, right, you have a certain sequence in you which predetermines what color your hair you can have, what color eyes you're going to have, when you start losing your hair, what age it'll turn gray. There's all kinds of things that are defined about you in your DNA. Okay, so these trends and correlations, whether there's causal factors or whatever, those trends and correlations represent sort of a model of the system you're monitoring. So understanding that DNA enables you to better understand not only your system, but when something starts going in a direction that needs to be monitored or corrected. So number 3 on this list, association discovery. So association discovery you might traditionally want to call like market basket analysis. All right, so that sort of puts in your mind a business use case, but I don't want to necessarily put it in a business use case. It's finding things that tend to co-occur together that you wouldn't expect. Okay, so these co-occurring associations also can become very predictive. Okay, finding these associations is important, again, for making the best use of your IoT data. So again, think of data discovery, that you might discover some new association. Data to decisions, that is, you see one thing. For example, if you want to build a recommender engine on recommending products or ad placement like we heard this morning. Okay, so you see that people who like this also like that. People who shop here also want to buy that. People who have these preferences tend to want to buy this thing. So you can find these associations and make good business use case out of it. But it's not just for a business use case. I had a colleague of mine who's applying this technique to predicting the intensification of hurricanes. So he's able to look at data when the hurricane is still far out in the Atlantic Ocean, the sea surface temperature, the shear speed across the hurricane wall, the atmospheric pressure, the temperature, all kinds of different factors, precipitation and so on, to predict much more accurately than the National Hurricane Center what the final intensity of the hurricane will be when it makes landfall. So I don't know why they don't do this, but his algorithm is better than the National Hurricane Center. And it's all done on market basket analysis by finding co-occurring associations that correspond with an intensity 5 hurricane or an intensity 4 hurricane or whatever. So there's lots of things you can do with this beyond just selling products on an Amazon-like recommender engine. And then for me, the big fun, the exciting part of all of this is the novelty discovery, finding the thing you didn't expect, finding that needle in the haystack, whether it's an exoplanet around a distant star or something else, finding the surprising, unexpected thing. So some people call that outlier detection. To me, that's just such a pejorative term. My students and I would just call it surprise discovery, because it's a data point that's in an unexpected place in your data set. And it's not traditional statistical outliers like a 3 sigma deviation from a curve, because imagine if you have all your data on a sphere. All right, so for example, what's the locations of all the people on Earth? Okay, so if you had a database with the locations of all the people on Earth, you would discover that they all live within a few miles of the surface, the mean surface of the Earth. There are very few people who live very far from that mean surface. All right, so now let's say you have another data point whose XYZ, so if your coordinate system is XYZ, not spherical coordinates, and the XYZ values are 0, 0, and 0. Okay, so that person, their X value is equal to exactly the mean of the X value of every person on Earth. Their Y coordinate is exactly at the mean of every person on Earth, and their Z value is exactly at the mean of every person on Earth. So therefore, they are not a statistical outlier, right? Wrong. I mean, they are definitely at a very weird place in the center of the core of the Earth. Okay, so outlier in this case, in that sense, doesn't make too much sense, which is why we prefer to call it a surprise discovery. Okay, that it is in an interesting, unexpected place. So all these things become discoveries for you, and whatever application domain you're working in. It might be again a novel thing, or it might actually be an anomaly. Okay, so it's something that's not working properly. Okay, so pay attention to all of these. Okay, so learning from our data is one of the key reasons we collect the data. We don't collect it to stick it in the box. Okay, so anyone seen the movie Raiders of the Lost Ark? They find the Ark, and then they lock it up in a box, and they nail it shut, and they put it in a warehouse and close the door. All right, and I swear there's some index number written on the outside. Okay, so that index number represents that thing. All right, so in some database, in some government spreadsheet somewhere in the world of Indiana Jones, there's an entry for a wood crate with an index number. But what does that index number do? It just tells you about where it is. It gives you no clue as to the intrinsic discovery potential and value of what's in that box. Okay, so focus on what's the intrinsic value and discovery potential of your data more than anything else. So moving forward, if I may. There we go. So consider these 3 case studies from a universe of possibilities that face us in this realm. Okay, so all these things are examples of what I would call dynamic, data-driven application systems. Dynamic, data-driven application systems. The first one is an astronomy example, as promised. So think of this again as a metaphor for a case you have. It's not necessarily an astronomy exercise here, astronomy lesson, as it is a data-driven application system example. So this is a true story about a telescope, which will satisfy the first of these 3 D to Ds that I mentioned earlier, data to discovery. So here's a telescope that's being built. Hello there. So this telescope is being built in South America right now. It received construction funding last year So it was in the President's budget in 2014, and several of us, including myself, have been working on this for over 10 years. The project scientists who conceived of this have been working on it for over 20 years. And so this telescope is being built in South America. It's too big to launch in space, so it is not a spaceborne telescope. It's going to do a complete study, monitoring of the sky repeatedly, night after night after night after night after night after night for 10 years. We call it cosmic cinematography. It's just basically going to take a picture of the sky repeatedly, as seen from South America, every night for 10 years, and it's going to be this movie of the night sky. And we're going to find everything that has changed in brightness or moved or somehow has done something dynamically from night to night over this 10-year window. So the image archive of this thing is going to be in the 200 petabyte range. We're actually going to create an extracted catalog, a database of all the objects and then different parameters, over 200 parameters: size, shape, color, position, brightness, and so on. And that database, which will be an SQL queryable database, is going to be about 40 petabytes. Okay, it's going to live on 30,000 separate servers, but it's going to look like one single SQL queryable database to you, the end user. So this is where the thing will live, down in Chile. And there's some astronomy use cases there. We don't need to read those specifically. It's going to take several years to build before it becomes operational. So this telescope has a 3 gigapixel camera, so you can't buy this one at Walmart. All right. The camera is fully 1/3 of the cost of the construction. Okay, over $200 million camera. It takes 2 bytes per pixel, so it's 1/6 gigabyte image every 20 seconds for 10 years. Okay, so I'd like to remind people that the Hubble, as we already heard today, is a pinpoint on the sky. It's extremely high resolution at that pinpoint. Okay, so for 25 years, Hubble has been studying the sky. We have several 100,000 images of the sky from Hubble. But this telescope, in the first 30 minutes of its operational 10-year lifetime, it'll accumulate more data in those first 30 minutes than Hubble has in 25 years combined. All right, big camera, big imaging capability, finding everything that has moved in the sky. And so we expect 10 million of these every night for 10 years. And I like to tell people there's not enough graduate students in the world to look at this. Okay? So what we need is something fast, some kind of fast statistical modeling software, because this is going to be a stream of data, okay? And like a lot of other streaming analytics problems we all face, and again, this is a metaphor, not necessarily your use case, obviously. Those things, once they've happened, you can't rewind them, all right? So once someone has come into your system and stolen your data, you can't rewind and say, oh, let's back up and patch that yesterday so he doesn't steal it an hour ago. No, wait a minute, that makes no sense. Same thing in our astronomical use case. If a star goes boom in the night, if it's a supernova or something happens, we can't say, oh, universe, time out, go back and rewind that for me again, I missed it. No. So we have to do fast analytical processing on these millions of events every night. And oh, by the way, if we can't keep up with the 10 million tonight, guess what? There's 10 million more tomorrow night and 10 million more the next night and so on. So you've got to find some way. And so why is that important? This is important for astronomers because we're trying to identify all kinds of interesting things, which was the astronomy use case slide that I didn't read to you. So there's all kinds of really interesting astrophysics that we'll miss if we don't process our data really fast. So case study number 2 is a little bit more mild and mundane by comparison to what I just described in terms of data volume, the Mars rovers. So Mars rover is more focused, I would say in this case, even though it's doing discovery, obviously, but the Mars rover is this little device that's running around on the surface of Mars pretty much autonomously making decisions what to do next. So I like to think of it as a decision engine. So even though, yes, it's doing discovery, but it's making a decision. So it analyzes the rocks in its presence, and it says, are these interesting? Should I stay here? They're not interesting. I should move on. Do I see a trend? That is, when I was there yesterday and I'm here today, I see a sudden increase in the amount of water in the rocks or the amount of titanium in the rocks. Maybe I should continue going up this hill or down that valley. So finding trends and patterns and anomalies and class discovery are all about what this little Mars rover is doing to make the best decision of where to go, what to do next. Okay, so whether this is a retail marketing example or a health monitoring system or a tsunami monitoring system or a credit risk fraud analysis detection algorithm, you're trying to find fast trends that are and events so you can respond to them in real time as much as possible. Okay, so I think of our little Mars rover here as this intelligent data gatherer, mobile data mining and autonomous decision support system And now the actual Mars rovers aren't doing all of these machine learning things in reality, but in my vision of the ideal Mars rover is going to be doing all of these cool things to make not only good discoveries, but good decisions. And so decisions, like I said, might be some of these things that you see at the bottom of the slide. Like, for example, stay here and do more. Do I continue my operations the same way I've been operating? Do I follow some interesting trend? Do I notify someone immediately, or can I notify someone later? Okay, so sometimes we just call that triage, right? So when you see something interesting, is it something you have to react to immediately, or can you wait later? So I like to refer to this as with another sort of play on words here. I call this going from sensors to sentinels to sense. Okay, so the sensors, again, in our IoT world, in our Internet of Things world, the sensors are everywhere. Okay, sensors are collecting data from everything. Okay, so we're collecting data. All right, so we're monitoring data from many different types of sensors. Okay, and again, in this case, Mars rover, but it doesn't have to be. And in that data stream, and hopefully close to the sensor, not somewhere else in a cloud somewhere, though you could do it that way, but if you want to have a fast reaction time, you want to have something close to the data, which is a decision engine. Business rules, let's say, that are doing those correlation discovery, class discovery, outlier discovery, association discovery. I'm finding something interesting here. What do I do now? There's a decision rule right there. That set of decision rules and machine learning application is a sentinel. All right, that's what I mean. So what is a sentinel? The sentinel is the guard on the castle that says, "Oh, the enemy's coming. Wake up, everybody." Okay, so this person, it's not their job to fight off the enemy. All right, their job is to alert everybody that the enemy is coming. Okay, so the sentinel has a set of rules that knows when should I wake everybody up, when should I not. Okay, I see a bright fire, a bright light over there. Maybe the enemy is burning the forest coming toward us. Oh, wait a minute, that's the sun rising. You laugh, but I had a student actually do this once. Their assignment in my astronomy class was to plot the location where the sun would rise every morning through the course of a semester. And hopefully they would discover how the seasons change. The position of the sunrise changes over the course of 3 months. Well, about 2.5 months into the semester, the student came up to me in my class, and this was the same exercise I gave year after year after year after year to hundreds of students. This young man came up to me. He said, "I think I made a mistake. What I thought was the bright light of the sun rising was a street lamp down the street from my dorm room." I said, "How can you mistake a street lamp for the sun?" Anyway, I think it was a good excuse for why he didn't actually do the assignment, but anyway. All right, so the Sentinel has a set of decision rules, and then it's up to something in the back end, whether it's a person or algorithms or something that makes sense of all that. And I'm getting thrown off the stage here. So our Sentinels are measuring, collecting data, applying decision rules, that's the Sentinel, and then enables us to make intelligent decisions based off those data. All right. So the framework I want to draw your attention to is something which has been part of sort of the lore, so to speak, in this field of DDDAS for several years. So in fact, this dynamic data-driven application systems goes back over a decade at least. So you can read about it on this website. And they have this framework, which is called the MIPS framework, which is measurement, inference, prediction, and steering. So it's pretty much what I said from sense to sentinels, sensors to sentinels to sense. So the MIPS is, the first is the measurement. All right, so you measure something, and then the middle part, I and P, inference and prediction, that's where all the machine learning cool stuff happens, where you infer what's going on, build a model, and do a prediction from that. And then steering, the last step is you move something. You move a person, or you move an ad on an online website, or you do something. So they're steering your resources, persons, processes, or things that you move into action based upon what you've learned in that process. So our big data analytics in the IoT is moving us from sensors to sentinels to sense making to ultimately dollars and sense making, hopefully. And so the last application is digital marketing analytics, and I'm going to be thrown off the stage, so I'll just sort of leave this to your imagination. But this is the big ROI, the big return on innovation. So we get data from many different sources in our marketing world, in our digital marketing world. Okay, so it's about what are people doing online, what's the weather, what's the context, is there a Super Bowl this weekend? So there's context, there's time, there's location, as well as clickstream. So combining all that information, you can automate that real-time sort of marketing delivery, that real-time marketing campaign delivery that's targeted specifically, uniquely to that individual. And that's sort of the gold standard of digital marketing, is that sharp, precision, personalized marketing. So making the long story short here, the final slide here is our data science includes all of these different approaches to data science, clustering, correlation, classification, outlier, all these discoveries to enable what we're hoping to achieve from our IoT big data, which is discoveries, better decisions, and insights about our processes, and therefore reap the value and the dividends that brings to us.